This is 2.5 halogenoalkanes. So the outcomes for this topic are, first of all, to be able to explain the variation in boiling points of the halogenoalkanes with different halogen atoms, to explain the variation in boiling points of the structural isomers of a halogenoalkane with the same molecular formula, to classify a halogenoalkane as primary, secondary or tertiary, to describe the laboratory preparation of a liquid organic compound such as a halogenoalkane from the corresponding alcohol, to describe the reaction of the halogenoalkanes with aqueous alkali, with ammonia and with potassium cyanide, to define the term nucleophile and outline the nucleophilic substitution mechanism involved in the reaction between primary and tertiary halogenoalkanes with aqueous alkali, to describe and explain, with reference to bond enthalpy, the relative rates of hydrolysis of primary halogenoalkanes with the same number of carbon atoms and different halogen atoms, to describe the elimination of hydrogen halides from symmetrical and unsymmetrical halogenoalkanes using ethanolic potassium hydroxide, and recall that chlorofluorocarbons or CFCs are a major factor in reducing the ozone layer and allowing harmful UV radiation to reach the Earth's surface. So, halogenoalkanes are saturated aliphatic compounds formed by replacing a hydrogen on an alkane by a halogen atom. And they're named according to the IUPAC rules, as we've seen before. So we name the longest carbon chain and add the suffix "ane". You name the halogen or the halogen atom or atoms as a prefix using fluoro, chloro, bromo or iodo. And if there are several, then you indicate their numbers with di for 2, tri for 3, tetra for 4, and so on, and indicate their positions by numbering the chain so that the attachment numbers are as low as possible, listing the halogens in alphabetical order. And then you indicate the presence of any alkyl groups in the usual manner. So first example here is 2-chlorobutane. And you can see here 1, 2, 3, 4 carbons, naming it from this end, 1, 2, 3, 4, so we get the lowest number. Then this is on the second carbon. And if we look at this example, 1-iodo-2,2-dimethyl-propane. So we want to name the chain that has the iodine in it. And you'll notice there's a little typo that should be CH3, but we'll forgive them. So the longest chain then has 3, which makes it propane. We have 2 methyl groups, which makes it dimethyl. There on the second carbon, and so that one's number 2, this one would be number 1, and then number 3. So it becomes 1-iodo-2,2-dimethyl-propane. So in the same way as the carbocations, the halogenoalkanes can be classified as primary, secondary or tertiary. So primary has 1 carbon atom bonded directly to the carbon atom that's bonded to the halogen. Secondary has 2 carbon atoms bonded directly to the carbon that's bonded to the halogen. And tertiary has 3 carbon atoms bonded directly to the carbon atom that's bonded to the halogen. So in our example here for primary, we see here that there's 1 R group, and an R group of course is just an alkyl chain. Secondary there are 2, and in tertiary there are 3. So compared to alkanes with the same number of carbon atoms, the halogenoalkanes have much higher boiling points, and this is due to the increased relative atomic mass of the halogen atom compared to a hydrogen, which results in stronger van der Waals forces between the molecules. And isomeric halogenoalkanes also vary in their boiling points. Tertiary halogenoalkane, for example 2-bromo-2-methylpropane, has a boiling point of 73, which is lower than the primary one of 101 degrees. So with increased branching, the molecules can't get as close, and there are fewer points of contact, so this results in weaker van der Waals forces and lower boiling points. So to prepare the halogenoalkanes, they can be prepared from alcohols, and it produces, in most cases, a liquid product. So the key techniques of reflux, distillation and use of a separating funnel and drying are used to obtain a pure sample. So for example, in this case we have butanol with sodium bromide and sulfuric acid, giving us bromobutane as our product. We see here the apparatus used. So there's a round bottomed flask being heated, and it would be heated with a Bunsen burner. It would be heated with a an electric heat source, one of those sort of things that sits around it like this, and the flask lowers down into it. We then have the thermometer here, so we can check the temperature that the vapour in here is at. We have the Liebig condenser, and then a flask to collect the distillate. Now, thinking about the reactivity of the halogenoalkanes, the carbon-halogen bond is polar with a slightly positive charge on the carbon atom, and it's attacked by nucleophiles. So an ion or molecule with a lone pair of electrons that attacks an area of electron density is known as a nucleophile. And nucleophiles include aqueous alkali containing hydroxide ions, ammonia, and potassium cyanide. So for example, if we look at the same compound, which is bromoethane, if we react with sodium hydroxide, we get the alcohol. If we react with potassium cyanide, we get a nitrile. And if we react with ammonia, we get the corresponding amine. And the mechanism of the reaction occurs via nucleophilic substitution and varies depending on the type of halogenoalkane. So if we look first at a primary halogenoalkane, and you only need to know about primary and tertiary for this, you see the nucleophile attacks the positive the end of the bond at the carbon, the electrons move towards the bromine, and we end up then with this sort of intermediate where there's a weak bond between both the bromine and the nucleophile and that carbon. So we draw the square brackets around it and the negative charge there to show that this is the intermediate, and the negative charge comes from the nucleophile. And then in the next step, the bond forms to the nucleophile and the bromine ion is released. Now with tertiary haloalkanes, we only have one thing involved in the first step, and that is the breaking of this bond, where the electrons move from the slightly positive carbon to the bromine. Here we have the bromide ion then, which is no longer attached to this carbon-cation intermediate, and the nucleophile reacts there, giving its electrons to the positive carbon, and we end up then with it being attached to the carbon-cation in place of the original bromine. So the rate of hydrolysis depends on the nature of the halogenoalkane, with iodoalkanes reacting faster than corresponding chloroalkanes due to the lower bond enthalpy of the chlorine to iodine bond. And halogenoalkanes can also react with alkali in ethanol to produce alkenes via an elimination reaction. And an example of this would be, this is bromopropane reacting with ethanol, and that's giving us propane, and you'll see that we have the sodium bromide is formed and then water is also produced. So it's elimination because you're removing that molecule from the original bromoalkane. So a hydrogen atom is removed from one of the carbon atoms adjacent to the carbon bonding with the bromine atom, as well as the bromine atom. So in elimination reactions, the atoms being removed are on adjacent carbon atoms, and a double bond is set up between those carbons, forming an alkene. With unsymmetrical halogenoalkanes, a mixture of elimination products is obtained. So for example, 2-bromobutane reacts with ethanolic sodium hydroxide to form but-1-ene as the minor product and but-2-ene as the major product. So the table summarises some of the reactions of the halogenoalkanes. We see that with potassium hydroxide, potassium cyanide, and with ammonia, these are all nucleophilic substitution reactions, but with ethanolic potassium hydroxide, it's elimination. The conditions for the first two, the hydroxide and the cyanide, are reflux. With the ammonia, you need excess concentrated ammonia in a sealed tube, and finally, with ethanolic potassium hydroxide. It's under reflux with ethanol as the solvent. And finally, chlorofluorocarbons, or CFCs, are a class of compounds which were widely used as refrigerants, propellants and solvents. However, they were discovered to contribute to the depletion of ozone, which is O3, in the upper atmosphere, which resulted in increased exposure to harmful ultraviolet radiation, and their use in these applications has been phased out as a result.